Seminarios. Hoy tenemos a Nacho Trujillo, quien acaba de obtener su plaza, así que para empezar, pues felicidades. Y justamente hoy nos va a dar un review de las galaxias masivas y su evolución en el tiempo. Así, cuando quieras. Por favor, si alguien tiene alguna pregunta entre medio, me pedís el micro para el stream, ¿vale? Gracias.
Okay, thanks, Anna, for the presentation. I would also like to thank the people here, and also I'm aware that there are many people following the presentation through the streaming, so I also want to cheers these people. So another talk about massive galaxies and evolution of these galaxies. So many of you, particularly the old ones, could ask, why do we need another talk about massive galaxies? So 5 years ago, it was absolutely clear what was the evolution of these galaxies. So they formed very early on, and they just simply passively evolved through the cosmic time. So this was the idea basically accepted for everybody 5 years ago. And in fact, they have good reasons for believing that this was the case. In fact, as I said, if one concentrate on the most massive galaxies, this kind of galaxies here, in the local universe, we see that objects that are more massive than 10 to 11 solar masses are basically elliptical galaxies, so they present these smooth pictures. 75% of those are early types. And from the stellar population, we see that they are all, they are metal-rich, and very importantly, based on the alpha elements, we see that the formation time scale of the stellar population was very short. So if you take all this information into account, the picture that you would extrapolate from the stellar populations in the local universe, you would say that the massive galaxies were formed very early on, and more massive the galaxy, it was even formed in a very short period of time. Okay? So the stellar populations in the local universe are compatible with that they form very early on and then just simply evolve passively. And in relation to the sizes, we also observe that the sizes of these galaxies are very large, compatible with being larger than 5 kiloparsecs in terms of the half-life radii. So if you join this with the fact that when we study the number density of these objects, so the amount of galaxies that we have per unit volume, and we study how these evolve with time, this is what these figures represent. This is the number density of these galaxies, okay, per unit volume, and this is the mass of these galaxies. If we concentrate on the most massive galaxies, okay, so this region of the diagram, we see that from the local universe, redshift around 0 to around redshift 1, basically, the number of objects per unit volume was already there. So, on one hand, the stellar populations are all formed and evolved passively, and also the number density of these objects have basically unchanged since redshift 1. So it was very natural. Then, using these two observations to conclude that there is the evolution of these galaxies is basically a monolithic-like scenario, so the gas collapse, form all these stars, and once this is formed, just simply evolve passively through time. So, end of the talk, so we can go back to work. So what has changed in the last 5 years? Question. Wait.
5 years ago, the standard model was that small galaxies formed first and merged with big galaxies later. That was the cosmological standard, not the picture you just presented.
I'm not talking about the cosmological model. I'm talking about the pure observations without any theoretical background to interpret them. So we will discuss this later. Okay? So just based on the pure observations, everybody that were working on data would say, this is the compatible with this scenario.
Everybody working on theory would have said the opposite.
Yeah, but we don't care about that now. Okay, so this was the picture. What was the thing that changed? The thing that changed, as always in astronomy, was that we were having access for the very first time to the possibility of study this massive galaxy high redshift and observe directly at early cosmic epochs. And what was the reason for this change? The reason for this change was that for the very first time, we got access to very wide, deep near-infrared data that allow us to detect these objects that are the most massive and also are very low in number, so we need large areas to cover in the sky. So what happened when we finally got access to, let's say, samples of thousands of these galaxies? What happened was this. What happened here? So the theoretical people frozen. Let me see. Oh, here it is. So this was the change. So we start taking deep images of these galaxies at high redshift. This is probably one of the deepest image of these galaxies taken with an extraordinary resolution from the ground base. So this is 1 arcsecond, okay? So this is a galaxy at redshift around 2, very massive, around 4 times 10 to the 11 solar masses. And this is an image taken with the Gemini telescope using adaptive optics using the K-band, okay? So the resolution of this image, the PSF, is 0.1 arcseconds, 3 times better than the NIGMOS image on the Hubble Space Telescope. And also, it was a picture that took about an hour to take. So this is an 8-meter telescope integrating with a fantastic resolution, this is what you see. So you find that the massive galaxy high redshift is extremely compact. So you can see that basically the bulk of what you can observe is 5 kiloparsecs. It's in 5 kiloparsecs, okay? In fact, when you estimate the effective radius of this galaxy, is around 1 kiloparsec. So around 5 times less than what you see in the local universe. This is another way of exploring this extraordinary size evolution. So here is a sample of around 1,000 galaxies. Here is the size, and here is the stellar mass of these objects. And this is for 6 different redshift beings, between redshift 0.3 to redshift of around 2. This line is the local relation, okay? So what we already know. So this is, for example, for an object of 10 to 11 solar masses, we get of the order of 5 kiloparsecs, and every individual point here corresponds to a massive galaxies at higher and higher redshift. Obtain this data with the Hubble telescope. So what you can see is that as soon as you move to longer and longer redshift, you find that at a given fixed stellar mass, the sizes of these objects are more and more compact. If you want to make this exercise more quantitative, what you can make is to divide the size of the galaxy you are observing versus the size that you would expect in the local universe. And when you do this exercise, what you get is this extraordinary size evolution with redshift that in particular for spheroid-like objects, okay, we find that at redshift around 2, the size of the galaxies was a factor of 4 to 5 more compact than what we observe in the local universe. When you do these numbers and you estimate the mean stellar density of these galaxies, you get stellar densities of the order of 10 to the 10 solar masses per kiloparsec cube. In the local universe, something that has such a mean stellar density is a globular cluster. So we are talking about an extraordinary change on the structural properties of this massive galaxy. Of course, this is an extraordinary result, and the first thing is to understand whether this result is robust or not. In fact, we were criticized by many people at the beginning, implying that this result is probably an artifact of the observations. And they were right on asking these questions, because as you go back in time, the cosmological dimming is taking an important role. It goes like 1 plus c to the 4. So if I move to redshift 2, I could have several magnitudes of dimming, and my super brightness could be compromised for that reason, and consequently my effective radii too. So how then are we secure about our size estimations? Well, this has been explored for many, many people. This result has been catching the attention of many, many people. I have just cited a few of those papers here. And you can see that this result has been found using all kind of facilities, from the Hubble telescope to very deep near-ground-based data, and from different wavelengths. And all of those, depending on the amount of time they were integrating, they got very similar results. Of course, you can argue that still the cosmological dimming could play a role here. Okay, so some people did the exercise of combining hundreds of these galaxies together, of these compact galaxies together, and explore whether there was anything like a faint super brightness around these objects that would appear when you integrate, when you stack many of these compact galaxies. In fact, doing this exercise, people did not find anything. So this is an stacking of many of these compact galaxies and then a subtraction of the objects, and there's nothing around this galaxy. So it looks like there's anything like a big halo surrounding these objects that would mislead our size estimation. So I think the sizes are now well measured, but what happened with the stellar masses? The stellar masses are difficult to measure. Stellar masses, in fact, are coming from the photometry. So people take a photometry from the UV frame, from the ultraviolet to the near infrared, and apply different stellar population models, and assume some star formation history, some dust models, several assumptions. So one could think, okay, the sizes are correct, but what you are failing is in the estimation of the stellar mass. In fact, as I mentioned, so it could happen that the galaxies that we find compact are not, the problem is not in this direction, the size, but in this direction, the mass. Okay? So people explore also this possibility and use different stellar population models. For example, in this panel, so these were the galaxies, and explore that using from Brusol and Charlotte, for example, to Marston models or new renditions from Brusol and Charlotte, the stellar masses that they were uncertain by a factor of 2 or so. Very, very much different from the factor of 20 to 50 that you need to move these objects to the local universe. You could also say, well, the metallicity is not clear. Try different metallicities. Again, the uncertainty is of the order of a factor of 2 in the mass. The dust, for example, could be wrong. They also tried different dust law, and also it was the range of variation of the mass was limited. And finally, you could consider, okay, you're using simple single stellar population models. The histories are more complicated. Use different histories, but again, they didn't find anything dramatic. So it looks that also the masses of these galaxies could be wrong by a factor of 2 to 3, but no, there's no way to say that these objects are wrong by a factor of 50. But of course, there's always people that say, until I get a measurement of the velocity dispersion, I will not trust that these objects are really massive. So there was a strong competition for getting the very first measurement of this velocity dispersion of this galaxy. And we did here the first measurement, we found that the typical velocity dispersion was around 250 kilometers per second, confirming that these galaxies are in fact massive. There has been another measurement finding of these values or even larger. Okay, so if we trust the observations, then we have to try to interpret this in terms of any theoretical background. So the theorists, from the very first moment, they suggest 3 different scenarios. In the first scenario, they said, okay, the galaxy, in fact, are compact, but they have a strong activity, nuclear activity, that eject all the gas from the galaxy. This change the gravitational potential of the galaxy and make the galaxy grow through a puffing up. And this is what they call the puffing up model. Okay. The other possibility that was suggested was that this galaxy merge through major mergers, and consequently they grow in size by the energy put on these mergers. And finally, there was other people claiming that what is going on is not major mergers, but a large number of minor merging that are continuously falling on these galaxies and making these galaxies grow. The second possibility, the major dry merger, was very early on rejected by the observations because people did not find enough major mergers to explain the size evolution. Consequently, we just keep the two models, the puffing up and the minor late merging. So I would explain what are the predictions for each of those mergers, and then we will see what do we find in the observations. In the first scenario, in the puffing up, as I said, the activity of the AGN ejects a lot of gas, okay? And this restructures the galaxy, and because you lose a lot of mass that is on the gas phase, the stars will expand and change the size of the object. The natural prediction of these models are that there is no stellar mass increase because you eject the gas, okay? Basically, no star formation would appear. The process is very fast, so you eject the gas with the AGN, and then the time that it takes for the galaxy to restructure and grow is less than 1 gigayear. There should be a strong decrease on the velocity dispersion of these galaxies because you have modified the gravitational potential, and it moved from very high velocity dispersion of around 400 kilometers per second to 200 kilometers per second. And finally, you should find a difference in the size of this object depending of the age of the stellar populations you are exploring. If you catch the object before the AGN phase, the object should be young and compact, okay? But if you catch the object after the AGN, it should be large and old. Finally, in the minor merging scenario, where many satellites are infalling on the galaxy, you would expect the following predictions. There should be a continuous increase and gentle increase on the stellar mass because of the accretion of the satellites plus the star formation that is connected to this infall. There should be also a gentle and continuous size evolution of the galaxies because of the infall of material. There should be a decrease in the velocity dispersion, but it should be very moderate because most of the material that infall into the galaxy should be located in the outer regions, because most of this material also have larger angular momentum and consequently, naturally, will be located out in the outskirts. And the size should not know anything about the age of the galaxy, okay? There should be some galaxies that you catch with old populations and another with young population, depending on the activity. But the sizes should be just simply evolve smoothly. So now we go to the observations and we can check how the observations fit much better in one model or in the other model. So let's start with one of the most clear predictions. So the size and the stellar populations are connected or not? Well, so we did very recently this year a work where we took of the order of a few hundred spectra, low resolution from the Hubble Space Telescope, and we explore in the size mass diagram for different redshift the position of galaxies that were divided into old and in young. So we took all the ages that we took from the spectra, and we took the galaxies that were the half older and the half younger, and we studied where the size depends on this separation in age. And you can already immediately see visually that the red, which are the older, and the blue, which are the younger, at all redshift basically are at the same distance from the local relation. Here we can see this more quantitative. This is the size evolution versus the redshift. The red dots are the old populations at every redshift, and the blue are the young populations at every redshift, and you can see that we don't see any connection between the size of the galaxies and the age of the galaxy. So whatever the mechanism that is making the galaxies grow in size doesn't know anything about the stellar population properties of the main objects. What about the stellar mass density profile of this massive galaxy high redshift? So if one take a look to the stellar profiles, so here we saw the stellar mass density, okay, versus the size, versus the radius of the galaxies. These green lines are for the local galaxies, for those that are spheroids and for those that are disk. And these are individual profile for high redshift compact galaxies. So here we saw this much better because we have stacked all the information. And what you can see is that the main difference between the stellar mass density profile of the nearby massive galaxies and the high redshift galaxies is the absence of these tails in the high redshift universe. Okay, so basically the central part of the galaxy is there, slightly denser, but very few. But what the main difference is that the high redshift galaxies do not present the long tails, the huge amount. So there is a missing of stars in the outer regions in the high redshift galaxies. And what about the evolution of these profiles with time? So Van Dokun and collaborators did a very nice piece of work here, combining thousands of galaxies, of massive galaxies, and observing how the stellar mass density profile changed with time. So this is the local distribution, and you can see that with time, the tail of these massive galaxies is growing and growing, okay? And it's doing very gentle, okay? It's like whatever is making the galaxies is increasing is because it's basically putting stars in the outer region, not modifying the central part of the galaxy. So this, as the previous evidence, this favor again the puffing up model and favor the merging scenario. So we have now at least two observational evidence favoring the merging scenario. What about the velocity dispersion evolution? This is another very clean test because it's not connected with the photometry or the superbrightness that you get. So what people have found is the following. So if you take galaxies of around 10 to 11 solar masses, okay, and you explore the velocity dispersion with redshift, you get the famous size evolution that we have already found, but you get a moderate evolution on the velocity dispersion of these galaxies, okay? So from around slightly less than 200 in the local universe to around 200 and a few at redshift 1, and at redshift above 1.5, just to 240 kilometers per second. So this was the result that we got here, and it has been confirmed by many other groups in recent years, and you can see here the points of these groups. So you can immediately see that the velocity dispersion of the galaxies is closer at high redshift to 200 more than to 500. That would be the natural predictions from these puffing up models. And because we discovered that it was closer to 200, we went to the Greeks, and we found that the Greeks also agreed that the velocity dispersions, the sigma, was 200. So we were completely sure that if the Greeks say that, we were correct. So it's, again, another observations that the merging model is more favored by the observations than the puffing up model. And now came another interesting piece of observation. So if the way this galaxy grows is stochastic in nature, in the sense that it's just because it's in falling of material, there should be some of those that would leave being untouched from the very initial early formation phase and just remain as they were today, no? You would expect, in fact, some models predicted that the amount of compact massive galaxies that one should observe in the local universe, like relics of that early epoch, should be of the order of a few percent. So we were very excited with that possibility, and then we decided to study where there was any single massive compact galaxies in the local universe that could be potentially one of these old objects being untouched by any infall of material since that epoch. So what we did was to go to the Sloan, and this is again the size versus the stellar mass, this time for all the galaxies in the Sloan at redshift 0. And you can see that most of the galaxies, as you expected, are large when they are massive, okay? So we concentrate on this region of the diagram. These galaxies are massive, but they are compact, okay? And we found 200 potential candidates of very massive and compact galaxies. From those 200 galaxies, it comes out that 150 were quasars, and they were misled, or so the size was basically the central part, and it wasn't representative of the host galaxy. But there were like 50 candidates here, okay, that were compatible with being galaxies, and very massive and very compact. So what we have, this represents only 0.03% of today massive objects, okay? So this is really, really much less than the natural expectation from these models of minor merging. So we decided to explore in detail how they look like, and we got time in the Gemini telescope, again, and we integrate very long, 1 hour, with high resolution in the Gemini telescope. And what we found is that when you observe one of these compact nearby massive galaxies, it has these funny shapes that look like more an S0, okay, something like a small disk with a big bulge. I would also add that it's very difficult to decompose these observations into a bulge and a disk. So we have not been very much successful on doing this. So it looks like that the nature is still not clear about how these galaxies are exactly. But we have obtained also the stellar mass density, the surface brightness in this case, versus the radius, and compare with the local universe normal size galaxies. And again, you can see that we found what we got also for the high redshift universe. So there is a slight excess of brightness in the center, but a clearly dramatic decrease in the outer region. So the amount of stars in the outer region is much less also for these compact galaxies in the nearby universe. So, but are those relics of the early universe? This is the main question here. And it comes here another surprise for us. What we did was to take the spectra from the Sloan, okay, and explore what are the features of the spectra of these compact nearby galaxies. So we found that the control galaxies were, as we expected, all. So this is the spectral range distribution. But the compact galaxies that we expected that they were really very, very old, it turns out that they were younger. So it was a total surprise for us. So there were no any single relic from the high redshift universe. In fact, in a index diagram where we can explore the age versus the metallicity, we find that the comparison sample, so the galaxies that are massive but large, using our indexes, shows the old ages and metallicities that we all know from the stellar population, but the compact galaxies are much younger, so around 2 billion years old, and also with high metallicity. So we are now doing a lot of follow-up to explore these stellar populations, but what we can conclude from this analysis is that this observation disfavor the emerging model. Is not clear what that they mean, because we expected some relics from the early universe that we don't find. And also, we find that disfavor the buffing up model because our objects are still compact, but they still are young. So something that doesn't fit very well. So what about the star formation histories of these galaxies? So what we find is that the massive galaxies has not been evolved so gentle and so smooth as normally we would expect from the stellar populations analysis of the local universe. And here it comes the results. So what we did was to take all our massive galaxies and construct the spectral energy distribution using from the UV to the near-infrared data, so from GALEX to MIPS. And something very interesting that I would like to show you is the following, because it has been there has been a lot of debate in the literature. So what you can see is that if you take the spectral distribution of different galaxies in the local universe, ellipticals and spirals, for example, from a LA type to an elliptical, you can see that if you don't go to the detail but the general shape, okay, and if you move in the normal regime from the optical to the near infrared frame, you would agree that these two spectral distribution looks very much the same. So you either go to the ultraviolet or you go to the infrared, so you can distinguish between the two populations when you have the level of information with typical photometry provides you, okay? So what you get then is that for objects that are classified as ellipticals, okay, with high concentration, high Sersic indices, we find that around 40% of our galaxies present excess of flash in the infrared, implying high star formation rates. Okay, so when we put this information versus redshift, we find that the star formation rates at high redshift of both spiral galaxies and elliptical galaxies were very much the same. So at redshift above 1.5, something that it looks like a spiral and something that it looks like an elliptical was forming stars at ratios of the order of 100 solar masses a year. Okay? It was only since then that the two populations start to separate, and in the local universe we see the huge difference in star formation rate that we observe between a spiral galaxy and an elliptical. But in the past, they were forming stars very strongly. And you can see that this has been decreasing, but smoothly with time, okay? It has not been just a strong burst event at high redshift and just since then evolving passively. So this, again, it's contrary to the puffing up model scenario. We have repeated these observations now even at high redshift, a redshift of around above 2 in different papers, and we have found also that the tendency still appears. So the star formation rate is very high for both families of galaxies at high redshift. So now comes another very interesting issue. So in the local universe, I said that 75% of the massive galaxies are elliptical, spheroids. But if you live in a universe where you have many bombardments, you would expect a strong morphological transformation. Okay. In addition, if you add to the fact that you expect that the natural morphology that massive galaxy or in general any galaxy when it forms should have, it should be more a disk-like galaxy because of the gas infall and the formation of the disk more than something that is an spheroid. So do we observe this? This is a work in progress, but where we are exploring the morphologies of 1,000 massive galaxies with redshift in detail using the Sloan, the ACS camera and the Hubble Space Telescope, and new data in the near infrared also from the Hubble Space Telescope. And we have been exploring how the morphology has changed with time. So what you see is that this is the fraction of different morphological types of massive galaxies with redshift. And you can see that basically the fraction, so in the local universe, we recover what everybody knows. So there is, if you go to the massive population, you have only a few irregulars. Around 30% of the galaxies are spiral, and around 70% are ellipticals, okay? When we focus on the most massive galaxies, about 10 to 11. But look how this has changed completely when you go back in time. In fact, if you move around above redshift 2, the ellipticals are not anymore the main population of massive galaxies, but they are below the disk-like galaxies. So it looks like the elliptical galaxy has been only the dominant population only since redshift of around 1. Okay, in the past, the massive galaxies were basically in nature a mixture between these galaxies and spheroid galaxies. So this is the situation. The observation disfavor the puffing up model, so it looks like the AGN is there, but the expulsion of the gas is not transforming dramatically the size evolution. The major mergers were, as I said, already discovered very early on because of the observations. So what we get is that the most likely scenario for the evolution of the structure of the massive galaxies is the infall of minor merging, minor satellites. So now we should move our attention to direct evidence of this scenario, because so far all the observations that we are collecting suggest this scenario, but only indirectly. So we would like to have direct proof that in fact is the accretion of satellites what is making the transformation of the massive galaxies. So what we can do in that sense? So the first thing is try to quantify which is the amount of infall of minor satellites that one would need to explain the size evolution. So if you get and you go to simple theoretical formulas that are coming from conservation of energy, for example, you can make quick predictions about how much the size of a galaxy and the mass of a galaxy should increase associated to the merging of another galaxy. Just energy conservation, for example. So these are predictions that are there. So we can take these predictions and try to measure how many of these merging would be necessary to explain the size evolution that we observe with time, according to the data. So we did such exercise, and as I said, this is just for having some numbers to talk about, no? So what you can see is that, for example, if you move to redshift 0.8, if the typical merger were a merger of 1 to 3, so the galaxy that infalls into the main galaxy is just containing 30% of the main galaxy, to explain the size evolution, we would need typically of the order of 3 to 4 mergers of this kind, okay? But if we were having infall of only 10%, okay, so if the galaxy were even more smaller, so the amount of mass that infalls into the main galaxy were only 10%, the amount of mergers, as you would expect, would be higher, with typically 7 mergers of this kind that would be necessary to explain the size evolution. Of course, the real nature do not take only 1 to 3 or 1 to 10. It takes a mixture and make the things more complicated. But I just put these numbers just you to have an idea when you are talking about what is the typical number of events that you would require to explain the size evolution. So how can we then test this directly? Well, we are working now on this, and we have just submitted to the journal a paper where we start exploring the amount of satellites, okay, that you can find around these massive galaxies with redshift. Okay, so what we are doing is to collect a large sample of massive galaxies at very different redshift, and we explore which fraction of those have satellites around. For satellites, we understand something that is within a radius of 100 kiloparsecs and in redshift compatible with the redshift of the massive galaxies, okay? So when you do that, you get a very interesting result, which is, so this is the fraction of massive galaxies that present a satellite, okay, of a given characteristic. Here, it's for galaxies that have typically 1 to 3 difference in, so the 30% I said before. So galaxies with satellites with 30% of the mass. And what we found is that this is very much constant. So this is a local universe measurement. So we find that it's only around 50% of the massive galaxies that present with redshift a 1 to 3 satellite around these objects. And it's constant. It doesn't change too much, okay? But if we move to objects that are only 10% of the mass of the main galaxy, we found that this number rises up to around 30% or so. Again, we should put this into numbers just to have an idea of what we are talking about. So we are talking about galaxies that are above 10 to 11 solar masses, so they are extreme in mass. When we are talking about a satellite, something like 1 to 3 satellites of this massive galaxy, we are talking about objects that are as massive as could be our own galaxy. Okay, so we are. It's not that we are exploring very minor satellites around that you would expect that basically all the galaxies should have one. So we are talking about the massive galaxy, the massive satellites around this galaxy. So we found that these numbers are very much constant with time and relative, not very large in number. Okay, so if you do again a very quick and dirty calculation, you get that these observations are compatible with about a factor of about 2 mergers of these kinds in redshift 2. So it's slightly less than what we get from natural expectation from the size evolution. So there is some tension there, but I just said that probably we are expecting something very complicated in terms of a lot of infall of even smaller satellites. But we are still far away from observing this observationally. So this is my summary, my conclusions. So the present day most favored picture would be something of this kind. You have a lot of gas that collapse and form a very compact structure of the order of 10 to 11 solar masses, which is well seen here. And then you have a lot of infall and accretion of minor satellites through the history of these galaxies that is mainly populating the outer regions, the tails of these objects. So with time, you start forming more, you start putting more and more stars in the outer region. So that makes that the central part remains basically unchanged, and that's why the stellar population's properties that we study in the local universe, which are basically representative of these parts, is compatible with what we observe. So basically, the core was already formed very early on, okay? So we move from here to here, basically through this minor merging. So this is what I would say at the present time is what the most favored picture observationally. Now, there's some open questions that it's for us to study, which is the accretion of minor satellites looks like very much the way of this is going, but we would like to make at least 2 direct tests. The very first one is, as I said, make an estimation of the minor merging rate in massive galaxies in redshift 4 to now, and try to not only counting satellites, but making the estimation of how many of those inform and at which speed. This is something that we cannot do observationally alone, and we need the input from the cosmological simulations to have an idea of how much time it takes for a given satellite to infall from a given distance to the main galaxy. Okay, so we didn't know, and this is the key ingredient to go from the satellites that we observe to the estimation of the minor merging rate. Okay, and finally, another thing that we should explore is to take the local massive galaxies and go to the outer region and measure the properties of the stellar population in that region and compare with the inner region. Because if we say that this outer region has been formed or put it there much recently, we would expect some kind of change in ages and metallicity. Okay, so I finish here. Very.
Let me propose you, go to the previous slide, let me propose you a completely alternative explanation.
Okay.
That for you to decide. You start from the beginning, the same observation, but the end, instead of being a elliptical galaxy, is the bulge of a spiral galaxy.
It doesn't fit.
Okay?
It doesn't fit.
And the question is that in many scaling relations, bulges of present-day spiral galaxies coincide with the compact galaxies.
True, but they are not so massive. So they are
equally massive. I mean, in the scaling relation, you can see I saw this in the paper by Alistair Graham in the recent review that he presents a couple of scaling relations involving radius, the size, and the stellar mass. So these are the parameters you're speaking about. And the bulges of present-day galaxies coincide with these compact galaxies. So the idea,
but except
the
for,
alternative in this case,
but not for the mass. This is basically incorrect for the, no.
coincide in the same.
You don't have any bulge, or very few, that have above 10 to the 11 solar masses. So most of the bulges are just a few 10 to the 10, the largest one. And we are talking about here the objects that, for some of them, are so massive as 4 times 10 to the 11. Which bulge are of this kind?
There are a few. I mean, there are a few, but you also have a few compact galaxies. I mean, not all the galaxies were like this. So you are comparing a few things with a few things. But in this sense, I mean, the evolution will be no increase in size. It will be the same object.
Well,
accreting
at some point, it's just a matter of wording, because imagine that you are correct and you are accreting satellites and form the disk. Okay, so this would be a way of evolving in size. So basically, the message that I say here is that the bulk, the 10 to the 11 solar masses, was basically unchanged, and you put matter outside. How this matter is dynamically, let's say, structure, I don't know, could be randomly or through orbital motions, but circular motions. So this is just a wording.
Maybe a missing element in this, which is really something I'm sure you know about it very well, is the gas.
Mm-hmm.
Because in none of your considerations have you explicitly discussed star formation per se and changes brought about by the fact that gas behaves differently from stars. I'm sure you're completely aware of it, but it hasn't actually come out in the presentation as such.
Yes, because observation of gas are still not very many. Okay, most of the people has been concentrating on first photometry, and now most of the effort is on measuring the velocity dispersion of the galaxy just to confirm that they were massive. Mm-hmm. But it is true that there's starting to be some velocities measurements coming from H alpha, for example, for this galaxy. And but the results are still not very much elaborated, so I couldn't comment very much on this yet. So what I can say is that we find, using indicators like the infrared data, that there is some star formation, important, intensive star formation going on at high redshift.
And it would affect the resulting densities, dispersions. It would affect many of the parameters that you're
It would depend on the amount of gas.
Sure.
So.
Just a comment. I suppose you know that already in the early 70s, people knew that the galaxies were smaller, although they have used radio instead of visible. Mm-hmm. The radio galaxies were also shown to be smaller. So in some sense, there was some discussion about this topic already 40 years ago.
I know, but I mean, the number of galaxies were so few that I would not claim any. Yeah, there were a few, less than 2, 3, 5, something like that. I mean, of course, there would someone at the 80s or something that say radio galaxies are compact, but you know.
No, not about compact, but in general, about the evolution of outside. No, of course, they have not any measurement of the mass of the galaxy, the stellar mass. They are that kind of that now it's more evolved. Also, as you know, because I was discussing with you, here we have the cosmology related to this problem. We don't measure the physical size of the galaxy; we measure the angular size.
Yes.
So in order to get
I would answer your question with a slide, because I was expecting. No, that's not true. I was expecting in any case, but no. Okay, so if the cosmology is incorrect, the size evolution should be similar, independently of the size of the morphology of the object. Correct? Yeah, so we should see that the same amount of evolution takes place for spheroid and for spiral galaxy. We don't observe that.
Yeah, no, and this also I wanted to comment.
Wait a second. So here it is.
Yeah, I know.
So these like galaxies evolve in size also, but a factor of 2 different. So this is a logarithm.
Yeah, no.
So this is dramatic.
I know if this is correct, this will be, of course, it will be saying something that the evolution of these galaxies is different from the elliptical galaxies. However, the method you use to separate these galaxies is basically the charge profile.
And also visually, we have repeat this with the morphological, and it's the same.
In this, well, you know that I have been working with your data, and I have playing with the parameters. You use the number of 2.5 to separate these galaxies and elliptical, and this is it's very sensitive, the selection of the galaxy to this number. So if you move the 2.5 to 3 or to 2.0, these ratios are quite different. So
that's okay. That's okay, because this is again against your suggestion of the cosmology. It's the main driver of the evolution. Because if you take different samples of the galaxies and you found different size evolution, this is against this idea.
I wonder, it's only a question, not an affirmation. I wonder whether the difficulty to separate elliptical galaxies and these galaxies at high resolution, because they can be confused, could be in some ratio responsible of this difference between what you find of the evolution of these galaxies and elliptical galaxies.
I would say it's minor. It doesn't explain the factor of 2. Could explain 1.3 or so.
Nacho, could you comment on this recent letter, a PGA letter that you co-author that uses data from GTC, where you have measured the width of all of these galaxies and turned out to be not as large as expected?
No, they would. No, wait. Because there has been some misunderstanding on those. So there has been currently a debate about the velocity dispersions. No, I'm going to phrase it much better. So the debate is the following. The stellar masses versus the dynamical masses. Okay? I don't know whether I have the formula here, but I would like to show you. Let me see. Here it is. So this is basically the way you would get dynamical masses if you were having velocity dispersion and sizes. Okay? So for the same mass and the same, for the same, okay. So if you are using this, and you got from there to, so if you get the dynamical mass using this, you will get the dynamical mass is basically the velocity dispersion to the square times the effective rate. Okay? Now, if you use exactly the same formula for the estimation of the dynamical mass, so calibrated using the local large galaxies, so it's basically this formula plus a constant factor here. Okay? So when you do such an exercise, just because of the galaxies are more compact, the dynamical mass would appear more compact because of the formula, if you use the same calibration factor. Okay? So all the debate that is taking place now is that when you use stellar masses derived from the photometry in the local universe, and you apply this formula, the dynamical mass are comparable with the stellar masses. Okay? You have dark matter or so, but basically it's the same. But when you use these formulas with the same calibration that in the local universe to estimate the dynamical masses of the high redshift galaxies, you found that the stellar masses of these objects, the high redshift, are higher than the expectation from the dynamical masses. And this is all the debate that is taking place now. I just said that if the problem is not related to the high redshift, but it's related to the that we don't still have developed a good calibration for the structure of this very compact galaxy, because we find the same problem in the nearby universe with the compact massive galaxies. So when we apply this formula, the dynamical mass, to compare with the stellar mass, even in the local universe, okay, we find a difference. So it's not related to any technicality associated to the measurement of the velocity dispersion. So there's something that we still don't understand, okay? A factor of 2 or so. So the stellar masses of these compact galaxies is factor of 2 larger than the dynamical masses. But I think at this very moment is calibration issue. So it's basically, I mean, and when you talk with the people that know about this, like Michele Capellari, for example, okay, Michael Capillari said, but you are crazy. How are you using something that was calibrated to other type of structure? So something that is less, not so compact. Okay, so things with care.
Well, I like the population, this population you have nearby, which can be quantified. And well, I understand that this is something. I mean, you have shown some sort of analysis showing the color and the metallicity of the system. You have said they are bluer and more metallic. What was it?
You mean the compact nearby galaxies? Okay. This one.
Yeah. So my question is maybe a bit naive and simple, but on one side, I like that you find this object because like this you can address not only the question how do they evolve for being smaller to becoming larger, interesting, also how the smaller were formed.
Mm-hmm.
But then I don't understand how you can have the same size or similar size, a similar mass, and you have something which is blue.
No. So the main difference between the blue and the red is the size of the galaxy. So this. So this is, so we took galaxies from here and we did exactly the same stellar populations analysis.
Yeah.
Okay. And these galaxies here in the compact region. Okay.
All right.
And so everybody knows, this is well known, that when you take normal control galaxies, normal sizes, 5 kiloparsecs, you get that the spectra is older. So you see here, it's much redder here than here. Sorry, much redder, much black. So you immediately see from a direct comparison of the spectra in the optical that there's an excess of blue light for the compact galaxy. So, and this, I thank you for your question, because this, I could link this with the previous scenario of Thomas that I started commenting here. So this was the expectation from the stellar populations analysis of the local universe. So basically, the massive galaxies were formed very early on and very quick. But you can see that these formation histories, so this is the look back time, this is the star formation rate, basically. So you can see that these objects, for a given mass, for example, mass range, they have some tails, okay? So it could happen that the massive compact galaxies that we observe in the local universe are basically the end of the tail of the formation of these galaxies, okay? So basically what the universe is telling us is that when you form a massive galaxy recently, it should form in a very compact phase, maybe.
Okay, and about the mass counting, I mean, you have also mentioned that may have sort of big burst that happens suddenly, which on the other side is very nice, but because they allow to detect them is a different set, so this could be a good test to look for them.
This is what we are trying to do now, yeah.
So, but if that would be the case, how much mass in gas you can play with in order to somehow keep the system evolving, and on the other side to conserve the mass, which is something, right?
Good question, I don't know. Something that we have to make the numbers. But for doing that, so the key is, so we observe that for an important fraction of the galaxies, the star formation rate is very high, as I saw here, okay? But if the galaxies were forming, for example, 100 solar masses a year continuously, the galaxy just a 1 billion year would be as massive as what we have now. So, so there is, as I said, a gentle trend, and the good question that could be is, this trend is compatible with which amount of mass created just by stars, okay? So I don't have the number on the top of my head, but I remember that wasn't like, it was like a factor of 2 at maximum, so it wasn't very large. So this decline star formation rate is compatible with just a small percentage of the, a small percentage could be as